Tang. Mingjin could not be present here. This is the second time that actually she participates in our session. We will be happy to welcome you here, but I know the situation is quite complicated in China with COVID. So the presentation concerns the hygroscopicity of fresh and aged mineral dust. And now we'll try to.
Dear colleagues, I'm Mingjin Tang, working at Guangzhou Institute of Geochemistry, Chinese Academy of Sciences. Today, I'm very pleased to give a presentation on hygroscopicity of fresh and aged mineral dust. First of all, I would like to thank chairpersons for inviting me to give this talk, and my students for conducting the research I'm going to present. Mineral dust is mainly emitted from arid and semi-arid regions, and could impact the earth system in many ways. It is estimated that around 2,000 kilograms of mineral dust aerosol is emitted into the troposphere every year, and mineral dust is the most abundant type of aerosol particles in the troposphere by mass. Interactions with water vapor plays a key role in the impacts of mineral dust aerosol on atmospheric chemistry and climate. Under subsaturated conditions, hygroscopicity determines the aerosol water content of mineral dust, and therefore affects its chemical reactivity and optical properties. Under supersaturated conditions, mineral dust can serve as cloud condensation and isonucleation nuclei, and therefore influence the formation and properties of clouds. In addition, aging process during transport would change chemical composition and therefore hygroscopicity of mineral dust. Currently, there are many techniques available for measuring hygroscopicity of aerosol particles. However, many techniques require the assumption of particle sphericity, or they are not sensitive enough to detect small changes caused by change in relative humidity. In other words, it is still a challenge to determine hygroscopic properties of non-spherical particles or particles with low hygroscopicity in a reliable and quantitative way. Unfortunately, mineral dust particles, in which I'm very interested in, are non-spheric and their hygroscopicity can be very low. To address this issue, we developed a new method to measure aerosol hygroscopicity using a vapor sorption analyzer, which is commercially available. The left figure shows a schematic diagram of this instrument. The instrument measures the sample mass as a function of relative humidity to determine hygroscopicity, and as a result, it has no requirement in particle shape. Furthermore, this method is very sensitive. As shown in the figure on the right, it can detect a relative mass change of 0.05% or even smaller. We conducted two types of experiments to validate the performance and reliability of this method. First, we measured the deliquescence relative humidity of six compounds, including ammonia sulfate and sodium chloride. Their deliquescence relative humidity ranged from less than 20% to almost 90%. As shown in the left figure, our measured deliquescence relative humidity agreed very well with reference values for temperature in the range of 5 to 30 degrees Celsius. In addition, we also measured hygroscopic growth factors of ammonia sulfate and sodium chloride at 25 and 5 degrees Celsius. As shown in the right figure, our measurements agreed very well with predictions by the EA model, To summarize, the method we developed could reliably measure aerosol hygroscopicity. In the first part, I'm going to discuss hygroscopicity of flash mineral dust particles. In this work, the new method we developed was used to measure hygroscopicity of 21 flash mineral dust samples. We examined 14 major minerals, including 5 oxides or hydroxides, 3 feldspars, 2 carbonates, and 4 clay minerals. In addition, we also examined 7 authentic mineral dust samples, including 3 Asian dust, 3 African dust, and Arizona test dust from North America. This slide shows surface coverage of adsorbed water as a function of relative humidity for quartz, albite, kaolinite, and 1 Asian mineral dust. As we can see from this figure, it is found that changes in absorbed water as a function of relative humidity can be very well described by the FHH adsorption isotherm, and this is true for all the 21 mineral dust samples we investigated. We found that hygroscopicity of flash mineral dust is very low in general, as shown in this figure. For most of the samples we examined, particle mass was increased by less than 10%. When relative humidity was increased from 0 to 90%. The only exception was montemolylonite, which has quite high hygroscopicity. As we can see, when relative humidity was increased from dry condition to 90%, the mass of montemolylonite was increased by 30% due to water uptake. We further found that hygroscopicity of mineral dust is positively correlated with their BET surface areas, as shown in the left figure. In addition, the surface coverage water is not correlated with. In addition, we found that the hygroscopicity is not correlated with soluble ion contents. This indicates that surface adsorption instead of dissolution determines the hygroscopicity of flash mineral dust. In the second part, I'm going to discuss hygroscopicity of slime mineral dust particles. In this work, we collected 13 topsoil samples from different locations in northern China. And this figure shows geographic distribution of our sampling sites. For the 17 samples, we measured their water-soluble content using ion chromatography. Mineralogical composition used X-ray diffraction, and the hygroscopicity used vapor sorption analysis. We found that those samples contained substantial amounts of soluble ions, and the mass fraction of soluble ions ranged from 0.4% to almost 84%. This is why they are called slime mineral dust, and the major soluble ions are usually chloride, sulfate, and sodium. Hygroscopicity of slime mineral dust particles was found to be highly variable, and some of the samples were highly hygroscopic, similar to sodium chloride. The mass growth factors at 90% relative humidity ranged from 1.02 to 6.7. These two figures plots hygroscopicity of slime mineral dust samples versus soluble ion contents, revealing a positive dependence. In other words, in general, Samples which contain more water-soluble ions usually display the higher hygroscopicity. We also use Isolopia 2, an aerosol thermodynamic model, to calculate the hygroscopicity of slime mineral dust samples we examined. And in this model, soluble ion contents were used as input in our calculation. As shown in this figure, it was found that Isolopia 2 could reasonably well predict the hygroscopicity of those samples at high relative humidity, for example, at 90% relative humidity. However, we found that the agreement between measurements and the calculation becomes significantly worse at lower relative humidities. In the last part, I'm going to discuss the impact of NO2 uptake on hygroscopicity of mineral dust particles. This figure shows the setup we used to study the reaction of NO2 with mineral dust particles. As shown in this figure, a mixed flow which contains some amount of NO2 and humidified was passed through a particle-loaded filter so that NO2 could react with particles on the filter. In our work, less than one layer of dust particles were deposited on the filter, and as a result, most of the particles, if not all, were equally exposed to NO2. In our experiment, the NO2 concentration used was 10 ppmv. The reaction time can be changed and up to 24 hours, and the relative humidity was up to 80%. After the reaction was stopped, we measured the composition of aged particles using ion chromatography and measured their hygroscopicity using vapor absorption analysis. The left figure shows changes in absolute mass of particulate water as a function of relative humidity for aged calcite particles. The right figure shows changes in the normalized particle water. The right figure shows changes in normalized mass of particulate water as a function of relative humidity, and the mass of particulate water was normalized to the mass of dry particles before heterogeneous reaction with NO2. As we can see from the right figure, for aged dust particles, significant hygroscopic growth happened at relative humidity as low as 20%, suggesting that calcium nitrate formed on calcite particles due to NO2 uptake was amorphous. In addition, the relative mass of particulate water at 90% relative humidity, when normalized to the dry particle mass, could reach almost 0.6. This slide shows the hygroscopicity of aged calcite particles as a function of time and as a function of reaction time. And as shown by the two figures, in these two figures, hygroscopicity is represented by the relative mass of particulate water at 90% relative humidity, normalized to the dry particle mass. We can see from these two figures that hygroscopicity of aged calcite particles increase with reaction time. Fresh calcite particles are solid and their hygroscopicity is very low. In contrast, after the reaction with NO2, an aged dust particle can take up a substantial amount of water and is transformed to an aqueous particle with a solid core. In other words, we can say that reaction with NO2 with calcite is a gas-solid interaction initially, and becomes gas-liquid-solid interactions as the reaction goes on. We have also explored the impact of NO2 uptake on high hygroscopic of feldspar and clay minerals such as elite. As shown in this figure, we found that after reaction with NO2 for 20 hours, increase in hygroscopicity was significant but quite small for elite and potassium feldspar. This is because much less nitrate was formed on those particles when compared to calcite. This may indicate that NO2 uptake only leads to phase change for carbonated minerals but not for other minerals such as feldspar and clays. We are also examining how reaction with NO2 would change hygroscopicity of authentic dust particles, such as Arizona test dust and China loss. In the near future, we also plan to investigate the effect of NO2 uptake on hygroscopicity of different mineral dust particles. My talk is over. October the 4th is a public holiday in China, and I'm staying in a small village with very limited internet access. Therefore, I cannot answer your questions online. However, you are welcome to send me emails if you have any questions. Thank you very much, and I wish you all a good time.
So as said by our colleagues, it's not possible to raise questions directly, but I think you can contact Mingjin if you've got some questions. I've got some about the system he uses for investigating the hygroscopicity, because I'm always concerned by the fact that in the mass determination, the particles are all stuck together, and I wonder how it may impact the uptake of water by creating some intra-particles connections, contact points. We know that it's very important regarding such high amounts of water uptake, but well. Now, so in his talk, Mingjin was talking about authentic natural dust as perspective, and Darya questions the use of proxies or natural dust, and she's raising the following question: how relevant is to use mineral proxies to mimic the atmospheric reactivity of natural dust samples? And she uses SO2 as a probe molecule.
Good morning to everybody. Airborne mineral dust of desert and volcanic origin represents a major component in the atmosphere. Thus, desert dust is emitted at 1,500 to 3,000 million tons a year. And to that, we can add from 30 to 250 million tons of volcanic material. These particles, when they get emitted, they represent a complex mixture. Thus, desert dust consists of quartz, elite, feldspars, chloride, gypsum, and many other mineral phases, while the volcanic dust is mostly aluminosilicate glass with the number of minerals that are embedded in this glass. And when these particles get emitted in the atmosphere, here we can see our round particles as desert dust, and this C-star particles represent the volcanic dust. They interact with atmospheric gases. And when we study those interactions, quite often we use the proxies. And by proxy, we mean the most abundant or the most reactive component. We do use proxies to simplify the system, to elucidate the mechanistic details of complex heterogeneous reactions, also to obtain a reliable, reproducible, and accurate thermodynamic and kinetic data, and also to just simplify the experimental conditions. We do it so much that in the recent UPAC evaluations, only about 30% of data on the kinetic data on heterogeneous processes was obtained using natural samples. The rest used proxies, which raises the question, how appropriate is it to use the proxies? To answer this question, we took 3 desert dusts. One is the Arizona test dust coming from the United States, the Ambur dust coming from Senegal, and Gobi coming from China. And we've got 5 volcanic samples from Iceland. And we observed their interaction with SO2 gas. The volcanic dusts mainly come from 5 volcanic areas. Thus, we have Hagavatna, Dinjan Sandur, Myrdal Sandur, Eyjafjallajökull, and Mælifell Sandur samples. And the first thing we did, we investigated its surface composition using XPS analysis. On this graph, you see the relative abundance by mass of different elements in our samples. Thus, gray is for Myrdal Sandur, Dinjan Sandur is in yellow, Hagavatna is in blue, Mælifell Sandur is in brown, Eyjafjallajökull is in red, Ambur is in dark blue, Gobi is in green, and in orange we see the Arizona test dust. And in the slide, you can see that our samples are rich in silicon, followed by aluminum, iron, calcium, magnesium, titanium, and sodium and potassium. And this elemental composition can also be represented in a percent oxide form. And this is actually a traditional way of representing the elemental composition. Thus, our Myrdal Sandur dust can be seen as a collection of oxides of silicon, iron, calcium, aluminum, titanium, and magnesium. Except for silicon oxide, all these oxides are commonly used as proxies to mimic the reactivity of natural samples. Other dusts can include clays, goethite, and calcium carbonate. We can also make a proxy. We can add the corresponding oxides and create a mixture of proxies that would resemble the natural dust. But we have to be careful because also, although it's customary, this representation of elemental composition is not the same, does not correctly depict the mineralogical composition of the dust. In other words, dust is not a collection of simple oxides. So what we did, we took our natural samples that we've discussed earlier here, and we used the proxies. So we used the simple oxides, but to them we also added a couple of clays, kaolinite, montmorillonite, and illite. We also added goethite, that is commonly used, and calcium carbonate. And what we did then, we observed its interaction with SO2 gas. We know that on the surface of mineral dust, SO2 interacts in the following manner. It can get adsorbed and get physisorbed on the surface. It can then react with OH group or with an oxygen from the lattice with the formation of sulfides. And it can then, that sulfide adsorbed on the surface, formed on the surface, can further be oxidized by an OH group or an absorbed atomic oxygen to form the sulfates. So in our research, we decided to quantitatively measure the number of sulfides and sulfates on the surface of different proxies and natural samples. And we did it by using this in-house developed aging system, which consists of 2 reactors where we placed our dust and we flow SO2 gas at 175 ppm at 30% humidity, room temperature for 1 hour. And then we wanted to extract sulfides and quantitatively measure it. But in order to do that, we needed a method to measure the sulfides and sulfates. And we looked through the literature, And I found a nice method by Zhu and all, an HPLC method, that claimed to separate sulfides and sulfates in atmospheric waters. And he uses a commonly used CAT column, which he coats with cetylpyridinium chloride, which makes this column polar and able to separate negative ions. He also uses a potassium hydrogen phosphate buffer, a phthalate buffer, that has a ring that enables a UV detection for the determination of our species. So when the analyte comes in, it's detected as a negative peak. We've applied the method, and unfortunately, we're not able to separate sulfides from sulfates, as we only obtained one peak. So what we did, we modified the method. We added a derivatizing agent in the form of formaldehyde. So our sulfides and bisulfides were transformed into hydroxymethyl sulfonate. And we can see it here. So now we separate sulfates from hydroxymethyl sulfonate. We applied the method, and we obtained a separate peak from sulfides and one for sulfates. So what we did next, we took our natural dust, Hagavatna dust, we aged it for 1 hour, we applied our method, and we saw this two nicely separated peaks. So we've created a method. Next step, what we needed to do, we needed to validate it to establish the performance criteria. And we validated the method for specificity as spectral purity. We assessed linearity. Our method was linear from 6 to 191 ppm for sulfides and 3 to 100 ppm for sulfates. The limit of detection was established at 0.32 ppm for sulfides and 0.68 ppm for sulfates. And the limit of quantitation for sulfides was at 0.64 and sulfates at 338. We then evaluated the method injection precision at about 5% for sulfides and 9% for sulfates. And our method precision was 12% for sulfides and 23% for sulfates. And this is a method precision from aging till the analysis. Our method was robust against the small changes in pH, mobile phase, column temperature, column age, and column lot number. And the solution, the extracting solution that we've got of our dust was very stable. It was stable up to 3 months, which was very convenient to work with. And finally, we needed 2 consecutive extractions of 1 ml of formaldehyde, of actually 40%, 1% formalin. And 1% formalin is 40% of formaldehyde. So we needed this 2 consecutive extractions of 1% formalin in order to get more than 95% of sulfides and sulfates from the dusts. So after our method was created and validated, we finally were able to apply it to our samples. And that's what we've got. We've got the various distribution of sulfides and sulfates. And we see that the distribution varies widely between the samples. We can broadly put them into 4 groups. We have some samples that don't form neither sulfides nor sulfates. And these are silica, quartz, and montmorillonite clay. Which means that this gas, the SO2 gas, could probably get physisorbed on the surface. We don't see physisorbed SO2 with HPLC method, but this process stops there. We also have a group of compounds, oxides of aluminum, iron, and titanium, and these proxies are commonly used in the literature. And you can see that they only form sulfides on the surface. So they react with the surface. But they don't, there's no, the following step, the oxidation step from sulfides to sulfates, either does not happen or happens very slowly. So we're not able to observe any sulfates. And then we have this a large group, and most of our natural samples fall in this group, that exhibit both sulfides and sulfates. So the molecule gets physisorbed, it reacts with the surface, and then it gets oxidized. Finally, we have a group of compound samples that only exhibit sulfates on the surface. And here the reaction mechanism is actually the same as for group number 3. The only difference is that this step, the oxidation of sulfides to sulfates, is fast. Therefore, we're not able to see sulfides on the surface. So what we were looking for is some kind of relationship between the pattern, the sulfides and sulfate formation of on the surface, and that in the natural samples. And we actually haven't found any. But then we thought that maybe if we mix the corresponding oxides, we'll get better results. So for Myrtle-Sundur dust, we theoretically calculated the amount of sulfides and sulfates that would have been formed on the surface. And we've got about 20 micrograms per meter square for sulfides and about 4 for sulfates. And then if we compare it to a real sample, we see that the real sample exhibits much more sulfides, about more than 90 micrograms per meter square, and much more sulfates as well. So about 35 plus micrograms per meter square. So we can see that theoretical estimation and the real amount of sulfides and sulfates don't really match. That could be for a number of reasons, but most probably the mineralogical surface composition of the real samples is not the same as that of the proxies. And it also could be due to the synergetic effect that we are not able to represent by just combining the oxides. So we would like to urge the scientific community to work more with natural samples, both to clearly evaluate the effects of real natural samples, but also to evaluate the relevancy of proposed proxies before making the far-reaching conclusions. Thank you.
Thank you, Darya. Do you have any questions? I guess yeah, okay. Go ahead, Michel.
Nobody has almost.
No.
I have questions if possible.
Okay. Yeah, okay. Look at the 3 comments.
Yeah, you have some in the comments and then I can wait.
Could you please turn off the, yeah, that's okay. So interesting talk, thanks. Take your points about representativeness. Iceland dust has so much glass material that it is going to be hard to use standard minerals to represent them. What is your comment on this?
This is absolutely true because the volcanic material in general is has a lot of glass in it. So in order to evaluate the additional mineralogical phases, we're looking at about maybe 10% of minerals and 90% of glass. And from that 10% of minerals, to get the small amounts of mineralogical phases is extremely, extremely difficult. Therefore, there were studies where volcanic dust was represented as amorphous glass, and that glass was actually made in the lab. And this is a very good approach because it it simplifies the system and gives us a reliable data. But the minus of this approach is that it doesn't take into account the different minerals other than amorphous glass. So it would be nice to still be able to quantify, at least qualitatively, what kind of phases we have in addition to amorphous glass, and establish the main ones and maybe do some experiments with them. We know, for example, that in volcanic glass we have olivine, we have magnetite. These substances, these samples are easily obtained. And of course, there are some others that are very difficult to obtain, but it would be nice to have this information as well. But yes, it's much more difficult to work with volcanic samples in this matter.
Glass doesn't account for heterogeneity of ash, and also ash is very different from eruption to eruption, even from the same volcano. The ash you used, isn't it already aged and thus not as reactive as fresh could be?
As a fresh well, it's hard to evaluate what is a completely fresh ash. If we look at the fresh ash as something we collect during the eruption, it still has already been processed by many gases during the eruption. And it is already aged, but it still can be rather active. For example, for the Eyjafjallajökull ash that has already been reprocessed in the plume, and we collected the sample. We didn't wash it, we didn't do anything with it. We've tested it. We had some sulfates on it on the surface already, and we subjected it to additional aging, and we still got a rather big absorption, formation of sulfates on the surface. So the volcanic ash can still be reactive even after it's been processed in the plume or in the atmosphere.
Okay, we have another one, Darya. So does the surface composition explain the different reactivity observed between volcanic ash and volcanic dust?
In this way, we have to distinguish the volcanic ash and volcanic dust. And if we look at it as a volcanic ash being something that's emitted right away, and dust as something that we've collected on a longer scale, there could be a difference in that reactivity. Hold on. I lost the question a bit. Yeah, the surface composition should explain the reactivity, but it's also the surface changes during the processing. So the changes in reactivity is likely coming from the fact that the surface is not that it changes on temporal scale. I don't know if I've answered that.
Yes, it is rained on. So yeah. So yes, it is rained on. Ash loses most of sulfates, which are highly soluble. Yeah. Okay.
Yes. That would be also very interesting to age the dust with any kind of mineral sample, and then explore its the reactivity of a sample that has been aged in a controlled conditions, and see how it reacts in relationship with other atmospheric gases.
Okay, last question, and then maybe you can answer, Darya, the question from the chat, by sending emails.
Yes.
So how do you think the influence of particle size, how the particle size can influence?
The particle size. Well, particle size can have something to... particles of different sizes might have different composition. For example, if this question has to do with the mineral dust of desert origin, our small particles quite often are clays, while the big particles quite often are quartz. So their reactivity might be completely different, just because they're different minerals, and they have different composition. Yeah. It's as Michelle Rossi said, it's a question of how long they take to be processed in the atmosphere.
Question? Yeah, come on. Yeah.
I'm glad that my question didn't come up within the. Oh no, I have a very simple question. Darya, you talked about sulfide to sulfate oxidation. My simple question is, what is the oxidizer of the sulfide?
According to the literature, that could be the OH groups that are present on the surface of dust, that are structurally present on the surface of dust. And that can be formed actually on the surface, since we work in the under relative humidity of 30%, we are constantly forming some OH groups on the surface. And therefore, these OH groups can oxidize our sulfides to sulfates. And another sort, no, that's what we thought on
Only oxidant possible is molecular.
oxygen. Yeah, the other.
So my question would be whether it's not about a reaction mechanism
For the
sulfide to sulfate conversion.
Yes. So here, wait a second. Can I change slides?
I think we can. You cannot. Yeah, I should make stop here actually to.
Do that.
Where is the presentation? This one, Darya?
Yeah, can I?
Yeah.
Okay, so for the final step, from what we've observed in the literature, sulfide to sulfate conversion here can go through the interaction with atomic oxygen, they say. So the molecule of oxygen gets absorbed on the lattice and interacts with an electron, and it splits basically the molecular oxygen into two oxygen atoms, which they call atomic oxygen, that then oxidizes sulfides to sulfates. I've lost sulfides to sulfates. And also from bisulfides to sulfate conversion, again from the literature, in the presence of iron atoms, well, it was suggested that bisulfides can react with OH group, and for that those OH group would oxidize sulfides to sulfates. Same thing for the, yeah.
So you should find H2O2 at some point.
For the, yeah, maybe.
Okay. Thank you, Darya.
Thank
so
you.
We can, if you have any questions, maybe you can discuss later on with Darya. Yeah. So we need to move forward and go to the next presentation, which is actually recorded. It was given by Taizhu Zhang, and the title of the presentation is Sulfate in Ice and Dust Particles at Desert and Downwind Areas, Comparison of Past and Recent Results.
Hello everyone, Taizhu Zhang from the Prefecture University of Kumamoto.